Hello everyone, welcome to Computer Science E7. This is lecture 10, Digital Cameras Continued. So I think last time I got myself a little bit flustered and I apologize if I made things a little bit more complicated than they need to be. So I just want to take a couple of minutes and just quickly review some of the major concepts that we went over last time. I'm not going to spend a lot of time on this, but just to make sure that I give myself a good opportunity to make it clear about some of these important things that are very important to digital photography especially. So one of these things that I'm referring to is this idea of having different sized sensors. So unlike film, where you had very set predetermined sizes such as 35mm film and smaller sizes that fit in much smaller cameras, we have a wider range of sensor sizes available in digital cameras today. And so even if we ignore the compact camera market, which has in itself a very wide range of sensor sizes, digital SLRs as well, even though they look like 35mm cameras of film cameras of yesteryear, actually have different size sensors of their own. And this causes a variety of things to happen to us as photographers. So first of all, we have a lens that can project a specific size image circle onto a sensor. But if we have two different size sensors, then we're going to capture different portions of that image circle. So we're essentially cropping out the sensor, and we get this idea of a crop factor that can arise from having these different size sensors. So if we have two sensors, such as a 35mm full frame one that's in red and a smaller APS-C sized or DX format sensor that's in blue, they have the same number of megapixels, and you use the same lens that's projecting this image of a mountain onto it, then it'll appear as though this smaller sensor is more zoomed in, because if you look at these two photos side by side, when they're the exact same size on your computer screen, it will look like you have captured more of the scene in this wider lens, or rather in this larger sensor, even though it is the same size lens. So it has the effect of looking like you are using a longer lens on this smaller sensor that you have. And we talked about even the comparison between not only digital SLR sized sensors, which is on the right here, and this isn't even a full frame sensor, compared to the size of the sensor in a typical compact camera, such as the one that can be found in the camera that can be borrowed from the Church Street lab, the Panasonic Lumix. And we talked about some of the implications of this. So if both of these sensors have the same number of megapixels, then that means that each pixel in the smaller sensor must also be smaller. Otherwise, you will have a disparity in the size of the pixels. And this also has a couple of really important impacts to us as digital photographers. First of all, the smaller sensor will typically have a much smaller dynamic range. So whereas the well size or the pixel size on the larger sensor is much bigger, so we can capture a much wider range of light, the smaller sensor will capture much less. And so this brings up the argument of a couple of physical limitations that camera manufacturers come up to and that we actually see as a result of some of the manufacturing processes. And that is that for the same technological year, or for the same technological generation, so if these two sensors were developed side by side, for example, and one is not considerably newer than the other, then the one that has the larger pixels will generally behave much better in terms of the quality. You will get better signal to, there's this concept of signal to noise ratio, where the higher the signal, the less noise will be apparent in the particular image. And the higher dynamic range we will have as well. And if we tie this into this last concept that we just discussed, if we have the same sized lens in front of each of these sensors here, then what is going to happen is that this much smaller sensor will appear to be much more zoomed in. It's going to look like we have a much longer lens on this camera than we do on this one. So to capture the same amount of the scene, or to capture the same field of view, in other words, on both of these cameras, or on both of these sensors even more specifically, we have to shorten the focal length of the lens for this one here. We have to make it wider. So whereas we might have had something like a 80 millimeter lens here for a nice portrait length, then we might have to get something like a 12 millimeter lens for that same field of view on this sensor on the left. And this had an even further implication of altering our perception of the depth of field in a particular image when we take a photo from two different sensor sizes. And so I know that one of the things that I was talking about is that last week I was saying that it's not necessarily inherent to the smaller cameras that they have this larger depth of field. It relates actually to the size of the aperture, and that's certainly true, and there's a variety of implications again here as well, that because this smaller camera has a smaller sensor, it must work harder, so to speak, in order to capture the same amount of light that this larger sensor does. So not only do we get this effect of extra depth of field, but what comes with that is this loss in this signal to noise ratio. And this is the same thing that we were talking about before, where if we are capturing fewer photons onto this smaller sensor, just because it's much smaller itself compared to the area of the much larger sensor, then we get this loss in quality. But there's another way to think of this sort of depth of field myth, as you might refer to it, and that is that it really comes down to the physics and the optics of the lens itself. So if you are using a particular camera, it doesn't really matter what kind of camera, but if you have a zoom lens on it, one of the things that you may have noticed is that the longer the lens on that camera, or the more you are zoomed in on that camera, the greater your ability to decrease the depth of field and get some very out of focus portions of the scene in the photo itself. And there's a reason for this, and that is that the depth of field is impacted by the focal length of the lens itself. So the longer the focal length, then the less depth of field, or the more depth of field, the less depth of focus. So this region that appears to be in focus will be narrower for longer lenses. And this is the same thing that we talked about in the optics lecture. This isn't anything different than what we referred to before. If you want to get the appearance of lots and lots of out of focus areas, you should use a longer lens, or you should use a lens with a very, very large aperture. And that same sort of thing is happening to us here, because in order for us to get the same field of view in this smaller camera that has a much smaller sensor, we have to use a much shorter lens than we do in this larger sensor, right? This isn't anything different than what we were talking about in this slide or even in this slide. The smaller sensor, in order to capture the same amount of information, has to use a wider lens. So it follows that if we are using a much wider lens or much shorter lens to capture the same field of view that we do for the larger sensor, then we are not going to have this, as much out of focus regions in this smaller camera. So it's not really because the camera itself is smaller. It's the result of all of these physical properties coming together and impacting the way that we can take a particular photo. Now remember that one of the ways that we can trick the physics, so to speak, so we can't actually, of course, modify the laws of physics or anything like that, but because this larger camera has the capability to stop down its aperture to make it much, much smaller, which means that the depth of field will grow, then what we can do is essentially mimic that depth of field of the smaller camera by making the aperture the same size. So if we consider it a ratio of the sensor sizes, then we can make the aperture the same size and then be able to get the exact same depth of field in both of these cameras. Now this example would break down if we were using a compact camera or a digital SLR that was much newer than the other, because then one would behave, or one would have better signal than the other, and so we wouldn't be able to make all of this math work out as well as it does in this particular example. And in fact, if you haven't read it, it's an interesting, if dense read going through this Clark Vision website, and where it discusses this exact thing when it references the signal-to-noise ratio and this exact depth of field myth, as he calls it. But it is interesting, but it's also very tough to get through because it's bringing all of these factors into play very, very quickly. And so it's something that is worthwhile, I think, to read, but be prepared to give it a few minutes to be able to go through it. Now, one of the other things that I mentioned briefly last time was the concept of ISO, or how we can simulate ISO sensitivity in digital cameras. So even though digital cameras cannot actually become more or less sensitive, we can trick it in a way. So you remember that we have these ideas of buckets for these pixels, where we have millions and millions of these small buckets that capture the light, or that capture falling water, to continue our analogy. And if we are to try to make it more sensitive to the amount of light that is presently there, then we can just double all of these values. So whereas before in ISO 100 we're able to fill up this bucket completely, in ISO 200 what was previously something that was only about this bright will now be multiplied by 2, so it will appear to be white. So only having this bucket, this is now the entirety of the range within our dynamic range, and what is possible to capture within the dynamic range for that particular ISO. So as we increase the ISO, we have fewer electrons that we are capturing, or rather fewer photons that we're capturing, that are being turned into electrons, and so we get this downgrade, so to speak, in the dynamic range of the camera. So this is an explanation for why increasing the ISO, while it is a good thing for us as photographers, because we can then increase our shutter speed, for example, and be able to capture photos at shutter speeds that we just couldn't do at a slower shutter speed, it has the downside of decreasing the quality of our image by some not insignificant amount. And so if you remember, I showed that DxOMark website where they actually they apply a lot of lab tests to a variety of cameras and actually show you the dynamic range that is available from each camera at all of these different ISO ranges. And you can actually see that at its lowest ISO value, all of these cameras have the best dynamic range that's possible from that particular sensor. Then as you increase the ISO, the dynamic range actually falls by about 1 stop. It's a little bit less than 1 stop because there's some other stuff going on here, but it does fall by about 1 stop. And the reason for that is that you are only capturing half the light, or you are only allowing yourself to capture half the light in each increase of the ISO. And so remember that because 1 stop of light is an increase or a decrease of about a factor of 2. So 1 stop extra light means twice as much light, and likewise for the other direction as well. And this means that just by having one of these, we are losing 1 stop of available light information. Any questions on this so far? Okay, yes?
Canon makes a range of lenses, S lenses. Would you apply a crop factor to those lenses, because they're specially made for only digital, not full frame cameras?
That's a good question. So Canon and Nikon produce lenses that are specifically designed for the cropped sensors. And so Canon has a line called an EFS lens, and I think Nikon's line is called the DX lens. And in each, so whereas here we have a lens, and I'm just going to use this as an example to answer the question. We have a lens here that is designed for a full frame sensor, which produces an image circle that covers that entire frame. These EFS lenses, or the DX lenses, actually have a much smaller imaging circle. So whereas this will produce this entire thing, the EFS lens might only cover the smaller blue sensor. So it's important to note that the focal length that these lenses provide to you, whether it's 10 millimeters or 20 millimeters or something like that. That's actually the focal length of the lens. However, you still could apply the crop factor multiplication or the multiplication factor to figure out the field of view of that lens as it equates to a lens that were on a full frame camera. So in other words, I have here an EFS lens that's designed for camera, and it's a 10 to 22 millimeter lens, so it's a wide angle lens. And this means that if you put it on, if you put it on a crop factor camera, it's going to have a very wide field of view. But in order for us to figure out what that same field of view would be on a 35 millimeter camera, I still have to multiply by the crop factor. So in this case, it's 1.6. So I know that this lens is approximately equal to a 16 to 35 millimeter lens on a 35 millimeter camera. Now, because the imaging circle is smaller here, that means that the lens doesn't have to be as large. So this lens tends to be a little bit smaller than the same sort of lens you would find for a 35 millimeter camera. So a 16 to 35 would probably be a bit larger than this lens as well. So even though the field of view appears to be the same, there are other physical differences as well. And I guess another one is that sometimes you just cannot simply put these lenses on the full frame cameras because they have extra little protrusions at the back or something like that that will actually hit, that will cause the mirror in the SLR camera to hit the back of the lens, breaking either the lens or the mirror, or something bad likely to happen, which would not be a good thing. Good question though. Anything else? Okay. So we talked about just some of the different types, or the major different types of digital sensors that are available today for us to use in digital cameras. So we have passive pixel sensors. The primary type is the CCD, so that's what you typically find in your compact cameras. We also have active pixel sensors, and we have the major type there is the CMOS sensor, and you typically find that in the larger cameras like digital SLRs. And so I mentioned that the difference between the two is just it's where a lot of the circuitry is applied. It's where the light gets amplified within it, and that's not really all that important to us. But what is interesting is the difference, I think, between the two. So CCD is one of the most popular, if not the most popular, sensor type available today, and that is because they are found in compact cameras, in digital cam, or rather in camera phones, and a lot of these devices where the noise, the amount of noise, is really going to matter. So these CCD imagers use a little bit more energy than CMOS imagers, but they are a little bit cleaner than the CMOS cousins. And this is a good thing for us because, as you know, with the size of these compact cameras and camera phones today, the pixels are absolutely minuscule, and so we need all the help that we can get to try to decrease the amount of noise within them. Another thing that we talked about from last time was this difference in the sensor size, how quickly a pixel can fill up with light if it is a smaller pixel than if it is larger. So a larger pixel will take longer to fill up with the same quantity of light than a smaller pixel, this is just another way of showing you that these larger pixels tend to have greater dynamic range than these smaller ones. So a lot of this stuff that we talked about last week is kind of abstract. We're using this analogy of buckets and to try to make this a little bit more accessible. And so now I want to make it a little bit more real with this. But don't worry, you don't have to be an electrical engineer to understand what I want to say about this. And it is this. It's relatively simple. So this is a schematic of 1 pixel from a CMOS digital sensor. This is just 1 pixel. So imagine that this is now several microns wide by several microns high. And you don't have to know what all of this stuff does, but just realize that there's a photodiode right here. This is where the light comes and hits. And so that registers a voltage. It's how the camera knows that there was some light that hits it. And then these devices that are right here are actually transistors. So you may remember, especially from the 90s, there was lots of talk about how transistors are getting smaller. It's the same sort of technology that you actually find in your computer processor. So transistors are what do the processing in a computer. And what's important to note about this is that there's 3 transistors for every pixel. And so what these do it doesn't actually matter all that much, but just realize that we have, for this one pixel, a tiny area that is able to actually capture the light, and then a lot of other junk that's not capable of registering, of capturing light, but is still necessary for us to be able to receive that picture in digital format. So for all of our talk about how these larger pixels actually matter, how if you double the area, you're able to capture twice as much light than you are in a smaller area, this is impacting us because we have this very small area that's actually capable of registering the light. So this is a very real problem, and this is something that manufacturers have had to try to combat. So if you were a manufacturer, how might we try to fix this sort of problem if we know that it's not possible to remove this circuitry, we can't make it any smaller, something like that? What can we do to try to, and here's a hint, focus the light that might fall on this entire pixel into this one little area? Any ideas? We have to focus the light. Tiny little lenses, yes. So we have this technology called micro lenses that exist on top of the actual sensor, so on top of the actual part that registers the light. And the job of these micro lenses is to focus the light that would have fallen on the entire pixel, to focus it down to one small portion of the pixel where that photodiode, or the small piece of circuitry that can actually register the light, actually exists. So one of these, so I'm always talking about how newer technology can help improve the capabilities of these small sensors. And this is a very real example of one of the things that can do it. As these manufacturers have gotten better at creating micro lenses, they've been able to make them capture more light or focus more light onto smaller pixels. So even though we may get larger, or rather more megapixels, therefore smaller pixels themselves, we are able to retain the same or even improve the signal that comes out of those pixels. And so this is just one reason why all of this stuff that I've been telling you up until this point, it is true, but it's something that also, as you know, I mean, there's a lot of other factors involved that you have to consider. So it's not just that, okay, well, this camera has, you know, fewer megapixels and it's the same size, so it must have better image quality than this higher megapixel camera. It's not necessarily true. There's increases in technology, such as this micro lens, that can help us improve the image quality of a particular pixel. Okay, so we have this one pixel, and this is slightly more accurate of a depiction of a pixel than this bucket that I've been showing you up until this point. But you can see that there still is an analogy where this light has to go down this well, as it's called. It's called a sensor well that is surrounded by circuitry. So this circuitry here is all of those little doodads and funky looking electrical things that we saw in the previous slide. And so the light has to travel down the well and into the photodiode itself in order to be registered. Now, there's something else that's important to note, and that is that if we have a deep well that we can see, that as you can see here, then this micro lens has to be able to always focus the light straight down into the well. And this can be problematic if you're using, say, a very wide angle lens where the light doesn't always come straight into the sensor. It may come at sort of these oblique angles from the center of the lens. And so that's yet another thing where we might get some problems from lenses or from cameras. So if you're familiar with vignetting, for example, where the corner of images get slightly darker. This is one reason why we might get a vignette for a particular camera and maybe not from a different one.